In Chapter 8, we have three topics: conservative and non-conservative forces, potential energy, conservation of energy. In high school, you learn the law of conservation of energy as an approach to solve problems, for which an analysis based on Newton's laws would be difficult or even impossible, because in some situations, the forces may not be known or accessible to measurement. Here, we focus on the importance of conservation law of energy as a remarkable statement about nature. Energy can be transformed from one form to another, and transformed from one object to another, but the total energy is neither increased nor decreased in any process. The total amount remains constant. Conservative and non-conservative forces. It is important to categorize forces into two types: conservative and non-conservative. Let's take a look at the work done by the gravitational force and its features. Considering an object under mg, the gravitational force near the surface of the Earth, moving from point A to point B, along the path of ACB and AEB, the infinitesimal work done by the force dW equals to F dot product with dr. Here, the force F equal to minus mgj, because the gravitational force is downward, but the positive direction of the y-axis is upward, so we have a minus sign here. dr split into dxi plus dyj. So the work done by the gravitational force W equals to integral parentheses minus mgj parentheses dot product with dr equals to integral parentheses minus mgj dot parentheses dxi plus dyj equals to minus mg integral dy from yi to yf. The yi is the initial position of the object, yf is the final position of the project. Therefore, the work done by the gravitational force Wg equals to mg yi minus mg yf equals to mg h. The h is the difference of the final position and the initial position. Sometimes we call it as the height. The feature of the gravity. 1. The work done by the gravitational force on an object depends only on the initial and final position or height, does not depend on the real path taken by the object. Second, the Wg on an object moving around a closed path equal to 0. Let's say the WAEBCA is a work done by the gravitational force around a closed path. It is equal to WAEB plus WBCA, because WAEB equals to mg times parentheses yi minus YF equals to mgh. On the other hand, WBCA equals to minus mg times parentheses y initial position minus y final position equals to minus mgh. So the total work done by the gravitational force around the closed path just equal to 0. The work done by the elastic force is another case that's similar to the gravitational force. Let's take a look at this experimental setup. An object is attached to a spring, and we set a coordinate this way. The origin of the x-axis is located as a position where the spring is not compressed or stretched. The xi is the initial position of the object. Xi is the final position of the object, according to Hooke's law. The force exerted by the spring to the object equals to minus kxi. So, the work done by the elastic force, W equals to F dot dx integral equals to minus kx dx integral from xi to xf equals to minus 1/2 k f square minus 1/2 k xi square. So Ws equals to 1/2 k xi square minus 1/2 k xf square. To our surprise, the spring force and the gravitational force have the same features. If the work equals to F dot dr integral around a closed path L equal to 0, we say the force F is a conservative force, or we say the net work done by conservative force on an object moving along any closed path is 0. Another definition for conservative force is that F dot dr integral from A to B equals to constant independent of the paths. Or we say the work done by a conservative force is recoverable. These two definitions for conservative force are equivalent. Here is an example of problem. A 2.0 kilogram block slides along a frictionless track from point A to point B. It travels through a total distance of 2.0 meters along the track and a net vertical distance of 0.80 meters. How much work is done on it by the gravitational force during the slide? If you apply the definition, work W equals to F dot with dr integral from A to B, you will find it will be difficult because the path taken by the object from A to B is a little bit complex. But the problem in this example is not so difficult. It's quite easy. Because we are supposed to find the work done by the gravitational force. The gravitational force is along the vertical direction. There's no work done along the horizontal direction. So the WV equals to mgh equals to 2.0 kilogram times 9.8 meter per square second times 0.80 meter equals to 15.7 joule. In Chapter 7, for an object in translational motion, the quantity 1/2 mv squared is defined as translational kinetic energy, K equals to 1/2 mv squared. Since the work W equals to 1/2 mv final square minus 1/2 mv initial square. Now, for a gravitational force, the work Wg equals to mg y initial minus mg y final. For a spring, Ws equals to 1/2 kx initial square minus 1/2 kx final square. All of these equations have the same form. So what should we do? We define another kind of energy, potential energy. We define potential energy, which is the energy associated with the position and configuration of objects, because work can be done if the position of an object is changed. Take a close look of the expression of the work done by gravitational force and spring force. If we define a work function U as Ug equals to mgy, Us equals to 1/2 kx squared, that is the potential energy, then the work done by conservative force equals to minus change of potential energy or degrees of potential energy. Potential energy means that an object has the capacity or potential to do work, even though it is not yet actually doing it. Potential energy can be stored for later use. Second, potential energy is relative. WAB equals to UA minus UB. The difference of potential energy U has absolute meaning, but to assign a particular U value to an object makes sense only if the reference U value is given. The reference of U is arbitrary to choose. UP equals to the conservative force dot product with the R integral from Rp to Ro, where the Rp is the position for the point P and Ro is a position for reference. We usually assume URO equals to 0 for simplicity. What is physically important in any situation is a change in potential energy, because that is what is related to the work done. A potential energy is associated with a system as a whole. potential energy is not something a body has by itself, but rather is associated with the interaction of two or more bodies, like the gravitational potential energy is associated with the Earth and the object. The spring potential energy is associated with the spring and the object. In one-dimensional case, if the force F as a function F equals to Fx is given, the potential energy function Ux can be calculated by the integral. Instead, if we are given the potential energy Ux, we take the derivative of the above equation both sides. Since integration and differentiation are inverse operations, we have Fx equals to minus derivative of Ux with respect to x. In three-dimensional case, we can write the relation between Fx, y, z, and u as Fx equals to minus partial derivative of u with respect to x, Fy equals to minus partial u partial y, Fz equals to minus partial u partial z.